Okay, class, we're back here. We're continuing our discussion of section 8.7, Taylor and Maclaurin series. We already looked at one example. Here's another example. So let me give you a moment to copy this example down. All right, so we have this function, which is 1 divided by the square root of x. There it is. And offhand, that function is not an easy function to work with, right? Because it's has a square root in there, and so if we could write this function as a power series, it could be useful. So, all right, we want to center it about a equals 9. Okay, we want to center it about a equals 9. So this is just, an example. We're going to choose to center it about a equals 9, and let's go ahead and see then the Taylor series. So of course, if I go to the ebook, section 8.7, here's the formula I'm going to be using. Right, now that is the Taylor series formula. A equals 9, and we have to compute derivatives. So I need to compute enough derivatives so I can determine the pattern for this. Once I determine the pattern of how the terms of the series act, I can get the series. And if I go back to the example here, looking at it a little more closely here. So since I'm going to have to find the derivatives of the function, okay, it would make sense to take that function and write it as 1 over x to the half power, or x to the negative half power, right, before I start taking derivatives. Okay, I mean, I could use the quotient rule, but it's easier not to if I can use the power rule. So, all right, so let's go to the solution here. Okay, so here in the solution, just like the previous example, I'm going to, hold on here. Okay, just like the previous example, I'm going to, compute the first 4 derivatives. And then every one of those derivatives I'm evaluating at 9. because A equals 9, right? A equals 9. So let me give you a moment to just copy things down here and let me know if you have any questions. I don't see, I could sort of, how to find derivatives, and I think you can see what's going on here pretty clearly. I found 4 derivatives, four up to the 4th derivative, and then I evaluated all those derivatives at A equals 9. So let me give you a moment to copy that, and please ask questions if you have any questions. Okay, so all right, so we're definitely looking at these terms, looking at these derivatives over here. We're definitely seeing a pattern. Definitely seeing a pattern here. It's an alternating series for sure, alternating power series. And let's see here. Hold on. This last one, actually, this is what I want to circle. Hold on. Okay, so of course, okay, so like y is 9 to the negative halves. Come on, give me some blue here. 9 to the negative halves power equals 1 over 3 to the 9th. 9 to the negative 9 halves power is equal to the 9 to the half power raised to the negative ninth. 9 to the half power is just the square root of 9. So you have square root of 9 raised to the negative ninth. That equals 3 to the negative ninth, or 1 over 3 to the ninth power. So that's how we're getting that. And again, you wouldn't necessarily maybe know to do that. But in your homework, if you had to find a power series for a function like this, you would likely be given a selection of choices, multiple choice, selection of choices, and you pick the right one. So sometimes, and that's kind of helpful, right? Because it gives you a clue as maybe as to what the pattern of the terms are. But you never want to force your answer, right? Because a lot of times these multiple choice questions, how many notice sometimes there's two very similar answers for a power series, or you have two answers that are somewhat similar. So you have to pick the right one, right? So that's why you want to be, patient before you select your answer. And that goes for the exam too, right? So okay, let's go ahead now and proceed forward. Now that we know the first four derivatives, let's put them in. And we end up getting a formula for our Taylor series. That's the formula. And here, all I did was I just followed the Taylor series formula given in section 8.7 in your textbook to arrive at the answer. Okay, I'll let you copy and let me know if you have any questions, please. Okay, so this is then the answer. So like in the homework, I believe you have a problem like this one. You'll have multiple choice. What is it? It'll be like a multiple choice problem, and you got to select the right series, the right power series, and how many think offhand this is some of the most beautiful math they've maybe seen so far? Well, I was hoping I'd get more of a response there. Put it this way, how about interesting? Ange, what do you think? Ange likes it. All right, Taj likes it. Okay. Certainly interesting, right? And Joseph agrees. And you know, you're basically now approaching, I mean, basically after this class, you'll be ready to take higher level math, 200 level math courses. I'm teaching 2 of them next semester in the spring. I'm teaching multivariable calculus, which is Math 280, and then linear algebra, which is Math 284. So yeah, it's good stuff. You're getting, you know. All right. Are there any questions before we move on here? All right, let me go ahead into the ebook. I want to go back to the ebook and look at that table real quick. Let me find it here. Book has a lot of nice examples. So the table shows the Maclaurin series for e to the x power, e to the x power. And let me just go to the whiteboard real quick here. Okay, so e to the x power can be shown to have this Maclaurin series. Which, if I were to write out some terms, hold on. One moment here. Just give me a moment, class. All right, we'll keep things. Okay, now one concept that'll come up in section 8.8 is the concept of Taylor or Maclaurin polynomials. So like, for instance, a first degree Taylor polynomial would be just 1 plus x. That's a polynomial of first degree, and 1 plus x is the first degree Taylor polynomial. Second degree Taylor polynomial would be 1 plus x squared over 2 factorial. Okay, because that would be the first 3 terms of the Maclaurin series. And then the third degree Taylor polynomial, so it's a polynomial of third degree, polynomial with degree 3. This would be the third degree Taylor polynomial. So it's just to help you get a feel for these series, it's helpful to look at the function e to the x with its Taylor polynomials, and that's what they show in figure 1 in the book. So let me just go to figure 1 here. Well, hold on. Are there any questions on what I wrote here on the whiteboard? All right. All right. So if I go in the book and locate figure 1, okay, they mention that the graph of the exponential function and those 3 Taylor polynomials are drawn in the figure. So in figure 1, you have the exponential function, which is the purple function, and then you have the first order Taylor polynomial, which is that line segment in black, the second order Taylor polynomial, which is the parabola in green, and the third order Taylor polynomial, which is the blue function. So all these functions approximate the exponential function reasonably well around x equals 0. But then as you move away from x equals 0, the Taylor polynomials start to get worse. In other words, they don't approximate the exponential function well as you move some distance away from x equals 0. Which of the 3 Taylor polynomials, T1, T2, or T3, does overall the best job in approximating the exponential function e to the x over the widest range of x values centered at a equals 0? Which polynomial, T1, T2, or T3, does the best job? All right, Taj has a thought there. What do you think? Which polynomial does the best job overall? T1, T3, T1, T2, or T3? Which one does the best job in approximating the exponential function over, a wide range of x values? So Ange and Taj think it's T3, and that's true. It is T3, and that should make sense because remember, the exponential function is equivalent to its power series. This power series, the interval of convergence, is all real numbers. So the exponential function is equivalent to its power series. And so the more terms we take of the power series, the better the polynomial is going to approximate the exponential function. So these are called Taylor polynomials or Maclaurin polynomials. And they're going to be of importance in section 8.8. Give me a thumbs up if you're comfortable with that, if that makes sense. Just give me a thumbs up. I'll look for it here in the thing there. All right, thank you, Sansar. Thank you, Taj. All right, thank you, Ange. Thank you, Javier. All right. Well, let us continue here. I want to do a look at another example. Now, this example we might not get through today, but we'll be able to do some of it. And what we don't finish, we'll finish next Tuesday. All right. So let me get the example. Okay, let me give you a moment to copy this example down. Okay, so let's take a look at what we have here. So in this problem, we have the product of, let me just change this font and get it. I can never get it right. Hold on. Okay, we have the product of an exponential function, e to the 2x, times this logarithmic function, 1 plus x squared. And we want to find the Maclaurin series for this function, e to the 2x times the natural log of 1 plus x squared. Now, we could, of course, find some derivatives of this function, go out to the third or fourth or fifth derivative and try to see what the pattern is, and then hopefully come up with a formula for the Maclaurin series for this function. But that could be difficult because this function here, I mean, it's not hard to, well, the derivatives, are going to grow in size, right? Because you're going to have the, like the first derivative, you would use the product rule. But then the second derivative, you're going to have to use the product rule twice, and then it's just going to build. And so it's not an easy way to go. What would be easier is to find the power series for e to the 2x and the log of 1 plus x squared, and then multiply those two power series together to find the Maclaurin series for, well, I should say, find the Maclaurin series for e to the 2x, that function, find the Maclaurin series for the natural log of 1 plus x squared, and then multiply those Maclaurin series together to come up with the Maclaurin series for our function e to the 2x times the natural log of 1 plus x squared. So if we like, let me now go to the whiteboard and well, actually, hold on, let me go to this next page. So this here is a handout that I created that has Taylor series formula, and then it has some important Maclaurin series formulas with their interval of convergence. And then there's a thing called Taylor's inequality below. We'll talk about that when we return next week. But this formula sheet, would you like to have access to this formula sheet? Okay, all right. Taj would and Ange would. All right, so and Jan would. Okay, all right. What I'll do is in the course content folder in Blackboard, I will under section 8.7. Once I've completed the recordings, processed them and put them in Blackboard there. I'll have a link there in section 8.7 under course content in Blackboard that will give you a link to this handout. And incidentally, I'll also make this handout available to you on the final exam. It'll be like an examity, there's a thing for supporting documents that you can access, like documents, handouts, and so forth. I'll make that available to you as well. Okay, all right. So let's see here. Now, the two relevant Maclaurin series are the one for e to the x and the one down here for the log of 1 plus x. So let me go to the whiteboard. Let me go to the whiteboard here. And let's see how we can make use of those Maclaurin series. So all right, so e to the x is equal to this series. And I'll write out a few of the terms just because I think it helps make things concrete. Okay, so let's say we wanted to do e to the power cheese. Cheese is my power. So x, x is a variable, right? Let's say my variable equals cheese. Well, all right, I'm going to substitute in cheese for x. And that's going to be my power series. The reason I do this is because what are we interested in this problem? We're interested in e to the 2x power. Now I could formally go through and derive that power series, the Maclaurin series for e to the 2x. But I don't really need to do that. I can make use of the power series, the Maclaurin series I already have for e to the x. So because e to the cheese, okay, equals this power series, so I'll let 2x be my cheese. Please let me know if you have any questions. And I could write this as 2 to the nth power times x to the nth power all over n factorial. And then the terms would be 1 plus 2x plus 2x quantity squared over 2 factorial. I'm looking here. Well, actually, hold on. I can do better than that, right? I can do better than that. Let's see, 2 squared is 4. So I got, what, 4 x squared over 2 factorial. But, hold on here. Right. And so forth, okay? So this can be simplified to 2x squared. Okay, well, I guess I can go out one more. 8x cubed over 3 factorial. That's just 8 6x cubed. And so now I have my Maclaurin series for e to the 2x. Let's do it now for the log of 1 plus x. Let's do the log of 1 plus x. The natural log of 1 plus x, based on the table from section 8.7, that table with the Maclaurin series in it, that equals this summation. And that formula should be familiar from section 8.6. Okay, and that is just x plus, no, hold on, x minus x squared over 2. How many of you recall this one? from section 8.6. Okay, it's an alternating series. Just thinking here. Yeah, yeah. And so if I wanted to do the natural log of 1 plus x squared, I would replace the x with x squared. See that? There's smoke. Don't worry, my house isn't on fire. It's just someone's cooking in the background here. Okay. And so if I write out some of the terms of that series, I'd have x squared minus x to the 4th over 2 plus x cubed over 6 minus and so forth. So you see, this allowed us, we have Maclaurin series for both of the functions that we're interested in. Let me see here. Oh, thank you, thank you. Good catch. This should be a 3. Who caught that? Who caught that? Thank you. Thank you, Taj. You're right. That should be a 3. So the next step is then we have to now, now that we have these two Maclaurin series for e to the 2x and the log of 1 plus x squared, the next thing we have to do is multiply those two power series together. Those two power series together. Those two Maclaurin series, we have to multiply them by each other. And I'm going to show you how we do that when we get back from our Thanksgiving break next Tuesday. We'll continue this example. Are there any questions before I stop the recording? Okay. Okay, I will stop the recording then. Wait, hold on. Oh, thank you. Another error. See, well, you can't think about two things at once. I don't want to go over too much on time. Hold on here. Thank you. Thank you, Ange, and thank you, Tosh, for, let me just double check here. Give me a moment here. Okay, this is right. That last term there for the log of 1 plus x squared should be x to the 6th power over 3. Well done. Well done. Are there any questions before I stop the recording? And we'll continue this example then. We'll finish up this example next Tuesday. Okay, great, great. I'll stop the recording.